Hello, this is Eric Jansen, and I'm here to present my final project for CSCI E-185 Big Data Analytics. And the topic of my final project is Storm and Twitter. Storm and Twitter is a match made in big data heaven, as we will soon see. Twitter is the embodiment of streaming big data. It provides a streaming API from which you can continually read data, off the stream. It's an HTTP-based API. In other words, you send a GET or POST request to Twitter, and it returns to you what is effectively a infinitely long web page, which never finishes loading. Excuse me. In order to process the data, you need an HTTP client that allows processing of the incoming HTTP content before the entire page is loaded. Some clients don't do that, but a lot of them do. Like Apache's HTTP client does. Twitter4j does. I wrote a small standalone application just to test the Twitter API before I began this project, and I used the Apache HTTP client for that, and it worked great. And Twitter4j also works great. Excuse me. The tweets, which come in from Twitter, are JSON. It's a JSON construct. So it's who doesn't love JSON? So it's easily parsed and managed. Twitter has several different kinds of streams, and the one that we're interested in is what's known as the filter stream, which is a stream where I tell it what kind of data I want. In other words, based, like if I give it a keyword or a phrase, I want Twitter to send me only tweets that have that keyword or phrase in them. As I mentioned, Twitter4j, that's what's being used to actually talk to Twitter from the Storm application. Here are some statistics about Twitter, some things that even surprised me. Active users, over 500 million, 100,000 new ones every day, 58 million tweets per day on average. I think that's actually low because it takes only 5 days to reach 1 billion, so maybe they're off by about a factor of 4 here on the average. But as you can see, there's some pretty amazingly large numbers here. 9,000 tweets per second. That's a lot of data. So there's no doubt that Twitter is a fire hose of big data streams. It's quite impressive. Storm began as a project at a company called Backtype that was led by an engineer named Nathan Mars. When Twitter acquired Backtype in July 2011, it immediately pushed Storm right to the front of its things to get out there, and they did. For good reason. Storm has got a lot of really interesting and powerful capabilities. It performs distributed real-time computation and stream processing, which is, Storm has done for real-time processing what Hadoop has done for batch processing. In fact, a lot of people just refer to it as a real-time Hadoop, which is a pretty good comparison. The Storm cluster. A Storm cluster is analogous to a Hadoop cluster, whereas Hadoop runs a MapReduce job. Storm runs what are known as topologies. And a key difference between the two is that a MapReduce job will eventually finish processing, and then that's the end of it. But a storm topology will process messages indefinitely. Once you start it, it could just run forever, theoretically, until it's either the hardware fails or someone kills it. But theoretically, once it starts, it's a continually running entity. In the storm cluster, there's two kinds of nodes. There's the master node and the worker node. And each of these nodes runs its own daemon to handle the various things that need to be handled by each of the nodes. On the master, it's called the Nimbus daemon, and on the worker, it's the supervisor daemon. The Nimbus daemon does a lot of, it's very similar to a job tracker in Hadoop. It sends data to the various nodes, to the various worker nodes. If one worker goes down, it redirects the work to a different, it reroutes the work. And it talks to the supervisor, which runs on each of the worker nodes. So the Nimbus talks to the supervisors, which are sort of the intelligence of the respective nodes, the master and worker. And they communicate to each other via a zookeeper cluster, which is stuck in the middle there. And each worker is responsible for executing its own piece of a topology. And here's a picture of that. Looks just like Hadoop, where you get Nimbus running on the master, supervisor running on all the workers, and zookeeper in the middle. And storm architecture. If you look at a drawing of the architecture, storm looks like a directed graph, and hence the name topology, which is quite appropriate for what it actually looks like. In this directed graph, each node performs some real-time processing, and each edge represents a stream in which data flows between nodes. Running a topology is similar to running a MapReduce job, which everyone in here is familiar with. And within the topology, the stream is the core abstraction. The stream consisting of an unbounded sequence of tuples, with tuples being the core data model, or the atomic unit of transport between the nodes and on the streams. Each node performs some processing on the incoming stream and then emits some transformed version of that from itself to the next node for further processing. You can have any number of these things chained together or running, you can have several at one level all doing something, and you can have some of them writing out to external applications, maybe a database or some other application. The nodes in Storm are called spouts and bolts. The spout is the top of the the node food chain, as it were. The spout talks to an external data source, in this case Twitter, and takes in tweets from Twitter and then emits them into the topology for distribution to the various bolts. The bolts do the work. A spout is a worker node, but it's sort of a high-level worker node. The bolts are the actual real workers, or they're actually doing the transformation of the data. And as I mentioned, the data is passed around as tuples to and from the spouts and bolts. This picture should clear up all the confusion. Here's a spout, so this would be connected to Twitter on this side, and this particular one is passing it to 3 separate bolts, same data or different data. and whereas this one is only going to this bolt, and then this bolt, these two bolts are then going to here where it looks like things are being aggregated perhaps. And then you could have any number of these things further downstream doing whatever it is you need to do. Some other features of the Storm architecture: spouts and bolts execute concurrently in a topology, and the amount of concurrence or parallelism that you want can be specified is in the configuration of the spout and bolt setup. And another interesting thing about Storm is that it guarantees there'll be no data loss. So the way it does this is each bolt must acknowledge the receipt of any tuple it receives. If it doesn't, the master node will reinsert the tuple back into the flow from the beginning to be processed. Of course, if it is acknowledged, the master just throws it out because it's been acknowledged. It's kind of an elegant, simple, brilliant way of doing it to guarantee that no data is being lost or not processed. As I mentioned previously, the tuple is the fundamental data unit. It's basically a list which carries named values. Each element in a tuple can be any type of object, the only requirement being that the object must be serializable, and it's very desirable for it to also be immutable, like Java strings and integers. I ran into a problem where I was accessing something that wasn't immutable while it was being serialized somewhere, and I was getting concurrent access exceptions, so I had to make immutable some of my data types that I was using. More Storm architecture, stream groupings. This tells the topology how to send the tuples between two nodes. Now, in the spouts and bolts, you've got multiple threads running, which they call, which are tasks, and how on a specific bolt, say it has 4 tasks, and another bolt has 4 tasks. Sometimes you worry, you want to know or be able to control which task sends its stream of data to which task on the other bolt. Sometimes you don't care, and sometimes you care very much. And it turns out in my application, I either care or don't care, depending on which bolts we're talking about. So there's several different kinds of stream groupings. The two that are of concern to me are what's known as shuffle grouping and fields grouping. Shuffle grouping essentially will randomly select the task in the downstream bolt and send it to it. This effectively load balances the work across the tasks as they're all being randomly selected. Other times you may want to use what's called fields grouping, which binds a task's output in one bolt to the processing task in the next bolt. This is very important in certain situations, especially in my application where I am counting the tweet, the words in the incoming tweets, and counting them in a downstream bolt. So I want all the words, certain words that are found to go to certain tasks in the downstream word reducer bolt, because each of these bolts has its own local map keeping track of data count, of counts for each word. And if I didn't use fields grouping and sent these words and counts out randomly, each task would have its own entry for a particular word, and they'd all be wrong because they'd all be just a subset of the total amount.